one approach to evaluating this power function is to take the data and calculate the natural log of x and the natural log of y and plot it up and see that it's a straight line. This is done in some cases, but in other cases we want to take a different approach. And what we'll do is to take the data x and y and we'll plot the data on log-log axes. And so when we do this, we're taking these data, so there's no transform applied explicitly, but when we select the log axis in y and the log axis in x, we essentially are getting a log transform. We're doing a log transform to the data. And typically it's a base 10 log transform as opposed to the natural log transform that we've just seen. So as just a refresher, the base 10 of log is equal to the natural log divided by the natural log of 10. So it's the natural log of x divided by 2.3. And to see how this works, let's take this example here where we plotted the natural log of y as a function of x. And so this was done in the previous video, and these are the data that we had in the previous video. And what we've done is to take the log of y, and that's these data, and so we plot the log of y as a function of x, and that's that's this plot here. So I did something similar with this table. This is the same data, same y values, and here I calculate the base 10 log of y and plot that as a function of x, and I get this plot here. And we can see that these are quite similar. If I go to this, let's see, x equals 2, then I get approximately y is 1, and then here x is 2. I come up here and get approximately y is equal to 2.3. So on the natural log, where the natural log equals 2.3, then I have this relationship between base 10 log and natural log, and it involves 2.3. So essentially what we have is these two plots are the same, except the y-axis differs by a factor of 2.3 because of this difference between base 10 and natural log. Okay, so in this case, I take the original data and plot it on these log-log axes. And what you can see is the curve is essentially the same shape as the curve that we just had in these two cases. The axes are different here though. This is 1 and 10 and 100, and what's going on here is that this guy is this is one log cycle, and so we go from log of well, essentially a log of 0, which equals 1, to a log of 1, which equals 10. So this plot, it's essentially the same as this plot, but instead of labeling the y-axis with the log of y, I'm labeling it with the actual values of y. And because I've taken this log transform, the position of the actual values of y here are transformed. They're moved around compared to how they would be if I plotted them on Cartesian axis. Okay, so that's why this looks the same as this plot. And what we want to do then is to apply it to this example, because here we've got this curve, and that's indicating that the original data are not an exponential function, but in this case we get a straight line when we plot it on a log-log axis, which indicates that it is a power function. So we'll go and apply the same kind of procedure that we just did to this log-log plot. And so when we do that, we get this. Here's natural log versus natural log, and here's base 10 log of y versus base 10 log of x. And we can see that the values of y here are the same as the values of y here, except they just differ by a factor of 2.3. And then when I go from, so if we go over here, the log of y is here and the log of x, and that's what I'm plotting. And then when we go here, I'm using these data, and I've got these log axes, and so it gives me a straight line, so that's indicating that it's a power function because it's log log, and I can get the parameters like so. When we have the data plotted up on these log axes, where I go, if I go to the log, or when I go to the value of x equals 1, then the value of x equals 1 is going to allow me to read the value of the coefficient off right here. So that's the coefficient, and then for the exponent I need to get the slope. So let's go to the next slide. Here's the plot, and in order to get the slope, what I need to do is calculate the change in y as versus change in x, so the ratio of change in y to change in x, but I need to do it with respect to log cycles. So from here to here is 2.2 log cycles. There's one log cycle, and we get another 1.2 out of the rest of this. So 2.2 log cycles that way, one log cycle this way. And you can see that I've covered over the axis here with this blue color, and I'm doing that so that I really, essentially, I don't need to know what these numbers are. I don't want to know, because when I get the slope, all I need is the log cycle, and that right there, that's one log cycle. That counts as 1 for the slope. But when I'm okay, so let me see. Let's go over here. Here's b is 2.2 log cycles divided by 1 log cycle. That gives 2.2. That's the value of the exponent. And the value of the coefficient, I let x equal to 1, and then I can just read it off the y-axis. And in this case, I do need to know what the value of the actual y-axis is, and it's 3.1. And so, okay, so here's the result. And now, one thing that I would urge that you do, there are plenty of places where you can make a mistake. So when you finish up with this, go ahead and substitute in a value of x, raise it to the power, and basically just solve for y. And so that would be a check. If you do it at 1 point of x and you get the right answer, then that's a pretty good check. And if you do it at 2 points, that's a really good check. So I would urge you to always check your results.